Hello and welcome back. In this video we're going to talk about relative isotopic and relative atomic mass. If we wanted to measure the mass of an element, it might be convenient to measure the mass in terms of the mass of the proton. Well, the mass of the proton is 1.67 times 10 to the minus 27 kilograms, which means the kilogram is a very unwieldingly large unit to measure atomic mass by. So you might think a better alternative is to measure it relative to the mass of a proton, where one proton is one atomic mass unit. And that almost makes sense, but we have to be really careful. And the reason was pointed out by Albert Einstein. In his famous formula, E equals mc squared, he pointed out the equivalence of mass and energy. In some circumstances, the two are interchangeable, and one of those examples is between the constituents of an atom being together and the constituents of the atom being separated. So, for example, when an atom nucleus is separated, the constituent parts actually have more mass than they do when they have together, and that's because the binding energy, some of the mass that they have separately converts into binding energy through E equals mc squared to form the finished product. Now that means that a lone proton by itself has more mass than a proton inside a nucleus. So it doesn't make sense to define an atomic mass unit relative to the mass of an unbound proton. We actively have to look for an isotope that's nice and stable, nice and abundant, but that is a conglomeration of protons and neutrons, and measure the atomic mass unit relative to that. So our mass standard for the atomic mass unit is going to be carbon-12. This is an isotope of carbon that has 6 protons and 6 neutrons. It's the most abundant isotope of carbon, and it is the most stable. Therefore, it actually is a very good standard against which to measure the mass of everything else. So, if one carbon-12 has an atomic mass of 12, then what we know is that the individual protons and neutrons in a carbon-12 would have an atomic mass unit of 1. Now, that means that 1 is 1/12 of the mass of carbon-12. And it seems slightly strange to constantly relate things back to, well, what proportion of the mass of carbon-12 does this have? Well, one proton has the mass of 1/12 of carbon-12. And so that means that if carbon-12 has an atomic mass of 12, then the proton is going to have a mass of approximately 1. And as soon as you do this, you realize something that is very, very useful, in that as each element increases, you find that there is a whole number progression of the atomic mass unit, element to element and also isotope to isotope. Now, this was first noticed by John Dalton. In fact, one of the things that he did was that he listed the elements in terms of their increasing mass. He was the first person to realize that that was a distinguishing thing between elements in the periodic table, was that their mass was increasing. Now, one neutron has an atomic mass that is ever so slightly higher than one proton. In fact, it's about 1.00335 atomic mass units higher. Now that means that even if you start with the mass standard carbon-12 and you add one neutron, then the atomic mass is not now going to be 13, because adding that one neutron, that 1.003, is going to take your atomic mass up to 13.00335. Adding another one and you get a little bit more. And so what you can see is that the atomic mass of different isotopes isn't exactly going to land on a whole number. Not necessarily, but it's often depicted when it's given to one decimal place as a whole number. But what you need to know is that for every single isotope, there is a relative isotopic mass for that isotope, which tells you in atomic mass units exactly what the mass is. So if I've got an element that's made up of more than one isotope, some of the atoms are going to be this heavy, and some of the atoms are going to be that heavy. Some of them are going to have this isotopic mass, and some of them are going to have that isotopic mass. So what is the average mass for that element? Well, that is the relative atomic mass. And what we need to do is we need to look at the proportions of all of the various different isotopes and what their individual masses are and find a weighted average. Now, the weighted average of the relative isotopic mass is going to be the relative atomic mass for that element. But we've got to get used to how these weighted averages work. So here is a real-world example. I wanted to know the weighted average of just how many legs the animals at the zoo had. And you can see I've got elephants, flamingos, and tarantulas at my zoo. Elephants, of course, have 4 legs, flamingos 2, and tarantulas 8. Now, it's not so easy as just to add up the number of legs. No, that wouldn't work. Or add up the number of animals. That wouldn't work. We need to take a weighted mean. So how I would work out the average number of legs? Well, the weighted mean would be, I would do the number of legs of an elephant times by how many animals there were, in terms of how many elephants there were. Add that to the number of legs on a flamingo multiplied by how many flamingos there were. And add that to the number of legs on a tarantula multiplied by how many legs, how many tarantulas we have. That is actually a count of the total number of legs over all of the animals we've got. And now we need to divide it by how many animals we've got. And basically we end up with 2.68 legs is the average number of legs that our animals have. The weighted mean for relative atomic mass is going to work very similar. What we need to do is we need to take the atomic mass or the relative isotope mass of each isotope and multiply it by how many there are of those. And how many is quite often the proportion in terms of what percentage out of 100 are of this mass. And once we've done that to all of the isotopes, if we've actually, rather than the number of animals, we've chosen the percentage abundance, we need to divide by 100 at the end. So here we go. This is something that we can have a go at. You can see that these different isotopes of hydrogen, for example, the normal hydrogen, the protium, is the most abundant, and there are very small amounts of deuterium, a second isotope. Now, these abundances are in percentages, and what we could do is we could take the relative isotopic abundance of protium and then multiply that by the percentage abundance of protium, add that to the atomic mass of deuterium multiplied by the percentage abundance of deuterium, and then divide it by 100%. That would give us the relative atomic mass. And indeed, that is some of the data that's displayed on the periodic table. Now, we'll go into the periodic table in great detail later, but take a look at each of those tiles. At the top, there's the number of protons, or the atomic number, but the number at the bottom, that's not the mass number. Not quite, because you can see it's a non-integer value. It's not a whole number, it's a decimal. And that's because it is the relative atomic mass. That is the weighted average of all of the isotopes. And you can see that it very rarely lands on a whole number. And before we talk about how we work this out, I just want to show you that the symbol for the relative atomic mass is capital A subscript R. So how do we find this? Well, in industry and in academia, we have a device called a mass spectrometer. And what a mass spectrometer does is it takes a vaporized sample, ionizes it, and then it accelerates it through a magnetic field. Now, the mass and the charge of the substance as it passes through that magnetic field will determine the amount of deflection it has, and we can measure from its deflection what its mass and charge must be, enabling us to work back and therefore look at, well, what proportion of the material came through was of this mass or that mass. And so you can see here, this is a sample of chlorine, and we've got some of it, the majority of it, coming through a mass in atomic mass units of about 35, and we've got a smaller proportion of it coming through at an atomic mass of about 37. And it means that we could work out the relative atomic mass for this element by just sending a sample through a mass spectrometer. So now it's time to put our knowledge into practice and have a go at some questions. The first three questions here are all the same format. You're given the relative isotopic mass of two different isotopes and their percentage abundance, and it wants you to calculate what the relative atomic mass of this element is. The final one requires you to work backwards to one of those numbers that was given in the question in the first three examples. It's given you the answer, wants you to work back to the question.